Welcome back. Um, Welcome back to Definitely Not Me. Yep, it's definitely not me. Okay. So today we'll be talking about how we can build a reliable RAG with LangGraph, right? Today we're gonna focus only on one aspect of the LangGraph, which is corrective RAG. This offers much more, benefit over the ordinary normal RAG you do, right? So it's much more relevant. Um, what this kind of RAG does is, if it does not generate a satisfactory answer, or if the answer and the context are completely not relevant, then it falls back and does a web search. There's actually a paper on this that says that that talks about the web search part. Yeah, so let's go ahead. First, let's look at what is LangGraph first of all. Then we're going to understand how LangGraph works through its components. And then we're going to see how we can implement the corrective RAG. And then we'll jump into the code, the workflow, its use cases, and then finally we'll end with what we can actually do further improve on it, right? Yeah. So LangGraph is a kind of a powerful tool for building, you can build multi-step workflows, and you can make an AI agent that does better RAG. So usually how it works is you have a question, right? You have a question. Your usual RAG goes like this. It takes a question. All your documents are stored in some kind of vector store. You retrieve them from the vector store. Then what happens is you actually directly pass that out to the LLM and get your answer. But here what we're going to do is, once our documents have been queried from the vector store, what we will do is we will use the LLM to compare the question and the documents it has received. If they are similar and relevant, okay, then we will consider only those documents for generating an answer. Okay, so if we find that even if one document is irrelevant, we are going to fall back to a web search to generate content for that document, for those documents which were irrelevant. So then we are going to pass this to the LLM, and hopefully we will get a better and more relevant answer. The reason why we are using LangGraph is because it comes with LangChain, and LangChain is already pretty easy to use with it has a lot of extensions and helper tools. So that's why we're using LangGraph for this. So let's look at the key components of the LangGraph. So I mean, this is our basic workflow. We're gonna have a graph to describe it. Okay, and then we're gonna have nodes. Each node is you can think of them as functions, right? And then there are some edges, and these dotted lines represent conditional edges, right? So what we're going to do is, once we start, we get a question, we retrieve the relevant documents from the database, and then we grade each document, right? So if all the documents have passed and all of them are relevant, okay, this is graded by another LLM or something. We do that. If all of them are fine, we go ahead and generate it. Else, for that specific document, I think in this case we are completely falling to a web search. We're going to use the API for that. We'll completely fall back to a web search and then generate the output, and then get the context from the web and give it to the LLM to generate a relevant answer. Yeah, this is only part one of three in the series. There are two other methods which complement this procedure, but we'll look at corrective RAG for now. Okay, how do we implement it, right? Again, this graph is there. First thing we do is document retrieval. Second thing we do is relevance grading. Third thing we do is web search if necessary, and fourth thing is answer generation. So I think that's it's already clear from the diagram, I guess. Yeah. So let's go on to building the CRAG workflow, right? Okay. So first thing we do is we make a we make our structure. We define a state for our answer, right? So first, we define a state, and the state could have each of these attributes. It could have a question, it could have a generation, which is the LLM generated answer. It could have a search flag for adding whether to search the web or not, and it could have a list of documents attached to it, and it could also have some steps which we can use later for tracking, like if we want to know a query has been using web search, or if it has, what sequence of steps has it gone through, we can know those steps. So the second thing will be actually implementing the functions which we saw earlier in each node, which is, I think, retrieval, grading the documents, generation, web search, and also choosing whether to generate or whether to search, right? Okay. The third function is the third part of our thing is building the graph actually. Yep, so we will just take all of these functions and the state, put it together, make a nice class. We will use the LangChain's state graph to do this, right? And then we will compile the graph into an executable workflow, and then invoke the workflow with an initial state, which is a question. So that is what we are going to do. Let us see how we can do that, right? Yeah, let us see. So in my code here, yeah, so the first thing we're gonna do is, of course, set up some APIs and all the things. I'm using LangSmith to track the execution of each cell and know the outputs, because I really don't want to include a lot of print statements in my code. It can make it hard to read. So that's why I'm using LangSmith to track the progress of all of these. So I will show you what LangSmith is in case you don't know it. So stay tuned, right? Then I just put these parameters over here, which is the local LLM. Like I'm using Llama 3 latest, and yeah, and apparently the people who have invented LangGraph, they have tested it with the 8 billion model of Llama 3, which will run on laptops, right? So okay, the next thing what we do is, the first thing what we do is choose a vector database to store our embeddings from the documents, right? So we take the documents, right? I'm using the recursive character text splitter, okay? Using that first thing, and I'm also using the web-based loader. So first thing we have is we have a list of URLs, right? We have a list of URLs. We are going to use this web-based loader to pass the contents of the URL and store it somewhere, right? And then I'm going to create a docs list, so I know each object. So each object in this docs list is apparently maybe some kind of a LangChain document class or something, right? Okay. Then what I'm going to do from this document list, which I've gotten, is I'm going to use the recursive character text splitter and split them into chunks, right? So that each chunk can get its own embedding, right? So I've specified some parameters here, like chunk size 250 and chunk overlap 10, right? And then what I do is I split the things, and for embeddings I am using Ollama embeddings here. LangChain supports Ollama embeddings, so, and I'm using this model for the embeddings, which is nomic embed text. It's quite popular, I guess. So yeah, and once I'm done with that, I create the vector store. You can also use, you can use ChromaDB or FAISS as well, FAISS, whatever. I read that FAISS has better performance than ChromaDB, but for the purposes of this video, I'm just going to stick to the scikit learn vector store database method. So yeah, we're gonna pass our document splits, our text splits, and also we're gonna pass our embeddings from the Ollama embeddings, right? The vector store will take quite some time to build, so it took around 2 minutes 20 seconds for me. And once the vector store is built, I get the retriever from the vector store so that I can call the invoke method on the retriever whenever I want to ask a question from the database, right? Okay, yeah. Then we'll move on to the tools, different tools, the functions, different tools we have, right? We have the retrieval grader. What we are going to do is we're going to make a prompt first, right? We'll define an LLM where we're using Llama 3 for grading the prompt, right? So we have, and we have a question and an answer or a fact, right? So what we ask the LLM to do is we ask it to give a binary score, yes or no, to indicate whether the document is relevant to the question, right? This is going to help us to avoid irrelevant answers, right? So we do this and we tell it that provide the binary score as a JSON with a single key score with no explanation, right? So Ollama, actually this chat Ollama has a thing called format JSON, right? You can specify the format you want here. So it will return it as a JSON string initially, and then some internal parsing happens, and finally the object is converted to a Python dictionary. It's basically a Python dictionary. JSON and Python dictionary are the same thing almost. So you get some kind of score here, right? Yeah, for example, I have provided information about some health document here in my URL, and then I asked a completely unrelated question to it. I asked like how to create a window using GLFW. This is something related to OpenGL or something. It's completely irrelevant, so I just gave it to I just tried invoking this retriever with the question I had earlier, and I tried getting the relevant docs from it, right? So once I got the document, once I got the relevant document, I tried attaching it to this thing, and I tried to call the retrieval grader, which I defined over here, right? It takes our prompt and it also includes the LLM and it passes the output, right? So what it did was I tried invoking this retrieval grader, and it finally gave me an Python dictionary with a score of no. So then what we're going to do is we're going to invoke this RAG chain with the documents that we had earlier. Remember, the docs was having information about the how to create a window using GLFW. That was the documents we had, and the question was how to create a window using GLFW, right? So I just asked it to print the generation, and it says that I don't know how to create a window using GLFW based on the provided documents, right? So of course it did not provide an answer to which it did not have access to. It did not have access to an info about like what GLFW is, right? So in this case, since the score is no, we also see that some kind of output from the model that I do not know how to do this. Actually, if you ask the base model, it will actually reply it to you. But we have we have prompted it in such a way that if it does not know the answer according to the document, it will just say that it doesn't know. So that's what is happening here. Yeah, and yeah, basically what we want to do now is if it doesn't know the answer, we want to do a web search. We want to use the web-based loader and load the documents for the web search, and then the model will give us an answer based on the web search, right? Yeah, so let's talk about the graph now, right? The graph part is kind of easy. It's kind of tedious and repetitive, but let's go through it. So I am using strict type type checking here, I want to be particular about what's, and I want to be particular that all of these are strings, and also that I don't face some issues again. So what we are using, the main thing we are using here is we are using the LangGraph. So you can, I'll link all the pip install requirements in the description. You can copy it. Yeah, so we have the line graph here. We're going to import these objects, the start, end, and the state graph. This gives us a framework to basically create a graph with many functions that you can call depending on the edge, right? You have conditional edges, you have just direct edges. Yeah, basically it handles that. And then we are also going to use Stabily for the search, right? The search APIs, we are going to use Stabily. Tably is good because it's free first of all, and you get up to 1,000 API, 1,000 free API requests. So I think that's why I'm using Tably. Yeah, we're just gonna specify our web search tool as Tably search results with k is equal to 3 to return the 3 most relevant search results, right? Okay, so then we have our graph state here, right? What our graph state will do is it will represent the state of our graph, obviously, and it's gonna have a question, it's gonna have a generation, it's gonna have a flag called search, and it's gonna have a list of documents. Yeah, that's what our state graph will have. And then we're gonna define methods to retrieve documents from the state. And also so what we're going to do is also going to keep track of what steps or what functions our chain has or process has gone through. So we're going to have a thing called steps as well, right? So every time it goes into a function, we append the name of that function to the steps of the state. So that's what happens in retrieval. We just get all of this data from the stuff, and yeah, we do that. Then we have the generate function. It just takes the question, it takes the documents and prompts the LLM to answer it, right? That's the generation, which is usually done at last. So we have another function called grade documents. Here what we do is we use our retrieval grader. We take our questions and documents. For each document, what we do is we ask the LLM, is it relevant to the question we are doing? If it is relevant, if the grade is yes, we append it to a thing called filtered documents, right? Yep. And if we find even one thing that is not relevant, we ask it to search. We turn the search flag to yes. Then we're going to return another dictionary of the state with the documents now being the filtered documents, question remaining question, the search remaining the search flag, whatever it was. And the steps, we're gonna append the steps. We're gonna tell that it has passed through this function. Then similarly we have the web search and the decide to generate. This I think you can read it on your own, it's not that lengthy as well. Yeah, so finally once we're done with all that, we create our workflow, right? We use this LangChain's LangGraph state graph, and we create a graph out of our thing, right? So now we add nodes to our graph, and yeah, we add conditional edges to it. We add edges, and then finally this is the graph. I've gotten this image using this command here. So that's how the graph looks like. And now we can actually use this graph. This is a practical thing, we can actually use it to test our thing, right? So and I tried testing it locally, but the problem was that for a simple question, it almost took 15 minutes. I don't know if that is because of my GPU or something else, but if you are using an API, it should be much, much faster. So, yeah. I tried testing it with this question. What are the types of agent memory, right? Okay, we can see the output over here on LangSmith. I think I terminated it because it was taking too long, but still the output is saved on LangSmith. Again, pretty LangSmith is pretty useful, right? So here we are on LangSmith. Yeah, this was the interrupt which I gave. So the first thing was it went through this retrieve retrieve function, right? And then it retrieved the documents. So if you can see, yeah, the documents were none initially because I haven't given it any. I was expecting it to do a web search to find out what are the different types of agent memory, right? So the AI answered, I don't know, fine. Then it went to the grade documents function. The documents were null, right, initially. So yeah, the steps were this, the input steps were this, and then we have this in the output step. So it has gone through the retrieve documents and grade document retrieval, and then it came out with the web search. Like it decided to do a web search. So you can see in this decide to generate, we have it called the decide to generate function, and the decide to generate actually suggested us a web search. So now we are going to do a web search. Tably API was called, Tably search API was called, and we got some kind of information from the internet about agent memory, I guess, right? So there's something AI agent journey, and it picked up some kind of information. And then here was the point where it took a lot of time to generate the answer. I'm not sure. Maybe it is because my laptop cannot handle Llama 3, I guess. Not sure. Or Ollama was not using my GPU. It could be any of those reasons, but you get the idea that we're going to finally get the output here. Oh, it actually did give an output, and it says that the types of agent memory are not explicitly discussed. However, one document mentions latent variable representations in something here, and it also gives us a link to which document it was talking about. And it says, okay, yeah, it did get some information. So I think we should try asking it relevant question, because our use case here is that we want it to perform better on our database, right? So yeah, I will be updating you with the performance once I stop the stream and try to run it again, because I cannot stream and run it at the same time. Yeah. Let's try running another prompt over here. Let's ask it what are the top 4 causes of death in the US. Okay, I do not want to know, but okay, but basically I have referred to some website, right? Let me just pull it up. It was about balanced diet, right? Yeah, so this was the website, I think. Yeah, this was a website, and I've seen some information here that the top 4 leading causes of this thing are these 4 things. So I want to be able to use this and get to know the top 4 leading causes. This would be a nice search. Actually, just it would just be a nice search. And then this also has some information that yep. I also want to ask this from this website. I also want to know that what kind of food can reduce the risk of a certain disease. So let's go ahead and try that prompt out, right? Yeah, let's try it out here. So we have, yeah, and what suggestions do you have to reduce their risk? So now I'm going to run this, right? um, it might take a while, but yes, it is going to run. Now we can see that we can actually go over to LangSmith and check our progress, right? We can actually check our progress over on LangSmith. So yeah, here we are. Let's go to LangSmith and let's run it. So yeah, here was my retriever. Yeah, 4 of the top 10 leading causes. It actually fetched the correct information, and I also asked what the suggestions you have to reduce this risk. And yeah, without exercise, see, it has picked up relevant content that Without exercise, they'll have a higher risk of obesity. And obesity is not there in the this one, but yeah, yeah, diabetes and high blood pressure. Okay, it is relevant, right? These were fetched from the vector store, right? And that happened in about like just for 4 seconds, because there was no involvement of Ollama over there. Okay, so this was our question. This was it hasn't gone through any steps yet, but the documents were fetched and put into the prompt for the LLM, right? So what is happening here is this was our prompt. It is going through a runnable sequence, and Olama is trying to answer our question correctly. I think this will take quite a while, so let us just look ahead. I'll come back to you when the output is ready. Okay, I think I figured out the issue why it was taking so long. It turns out that the answer was generated long back, but the function wasn't getting returned. So that I think that was the issue, right? So anyway, we have our output here. So the only question was, what are the top four causes of death in the US, and what suggestions do you have to reduce their risk, right? So the steps it followed was only the retrieval. So it got the document, put it there, and there was no other step needed. It went through the grading and all, I guess. Yeah. So yeah, the final output is, according to the documents, top four causes of death in the US are heart disease, cancer, stroke, and type 2 diabetes. And it also suggested some kind of it also actually suggested how to reduce their risk from the document itself. To reduce their risk, it is suggested that individuals adopt a healthy diet with a focus on whole foods, fruits, vegetables, protein, red meats, poultry, fish, and plant-based options. Additionally, regular exercise can help prevent obesity and metabolic syndrome, which are linked to the causes of death. Okay, that was pretty good. It actually gave the answer in a structured format. So let us actually verify if it is correct. So, healthy diet, whole foods, fruits, vegetables, and all that, right? Yep. Proteins. Yeah, I think it is. Yeah, healthy. Yeah, it actually saw these things, and yeah, red meats, poultry, chicken. So it has provided uh, good info based on the thing. That is good because it has analyzed the document, right? Yes. Okay, so I think that is it for the series. I will sort out this issue in the next part, and I will be implementing a better version of this RAG, and hopefully resolve this huge amount of time it took. I don't know why it didn't come out of the function, but yes, I will resolve that, and we'll check it out in part 2.